Well, in the previous lecture, we had discussed the T-invariant subspaces. We had given some examples, and we also discussed a theorem where we had seen that the characteristic polynomial of a restriction of a linear transformation divides the characteristic polynomial of the linear operator T. So let's first recall that theorem. That theorem stated that if T is a linear operator on a finite dimensional vector space, let T be a linear operator on a finite dimensional vector space V, and W is a T-invariant subspace. Is a T-invariant subspace of V. Then the characteristic polynomial of TW, which is the restriction of the linear operator T to the subspace W, divides the characteristic polynomial of T. Now we shall take in a small example on this theorem. Let's take a linear operator. Let T from R4 into R4 be defined by T of A, B, C, D. This is equal to A plus B minus C. Then suppose A plus B plus D. Then suppose 2C minus D. Then suppose C plus 2D. Then clearly this is a linear operator. We shall choose a basis and we shall choose a subspace, and let W be a subspace of R4 of this form, X, Y, 0, 0, such that X and Y are real numbers. Then for this linear operator, we will define the restriction of this linear operator T on this subspace W, and we will also show that this W is a T-invariant subspace, and then we will evaluate the characteristic polynomial of TW and show that it divides the characteristic polynomial of T. So then this T of X, Y, 0, 0 under this linear transformation. Now this is equal to, now T of A, B, C, D is given by this formula. So T of X, Y, Z, 0, this is equal to X plus Y. Again here it is equal to X plus Y. Then the third term is C and D, but here C and D are 0, so it is 0 and 0. So this is actually also an element of W. So thus T of W is contained in W. So therefore this subspace W is a T-invariant subspace. So now let TW denote the restriction of T from V to W. Now clearly, so let beta 1 which is equal to the set containing 1, 0, 0, 0, and 0, 1, 0, 0 be the basis of W. That can clearly be seen from the definition of W, because we can easily write this vector as in this standard basis E1 times this vector, then plus E2 times the same vector. So then we will get this xy00 as E1 times something plus E2 times one vector. So therefore, in fact, we can clearly see that this is a basis for this W. Now, since this is a subspace of R4, so therefore we can extend this basis to the base of R4, and also let beta, which is equal to E1, E2, E3, E4 be the basis of R4, be the base of R4. In fact, this E1 and E2 are these two vectors. Then this T, W of E1. Now, under that linear transformation T, so this actually T, W of 1, 0, 0, 0. Now, this in fact it is equal to 1, 1, 0, 0. So this is equal to 1, 1, 0, 0. And similarly, TW of E2, this is equal to TW of 0, 1, 0, 0. And this can clearly be seen again to be equal to 1, 1, 0, 0. So thus, the matrix of TW related to the basis beta 1, this is the base matrix. Now actually, this can be written as, this is 1 times E1 plus 1 times E2. And in fact, this also equal to 1 times E1 plus 1 times E2. So therefore, the matrix of TW is 1, 1, 1, 1. Now the matrix of T, this is equal to related to the basis beta. It has its columns as T of E1 related to basis beta. Then the second column is T of E2, the coordinate vector of T of E2 related to basis beta. Then the third column is coordinate vector of T of E3 related to basis beta. And the fourth is coordinate vector of T of E4 related to the basis beta. So therefore, we evaluate what is this T of E1. Under that linear transformation, this actually equal to 1, 1, 0, 0. And this can be written as 1 times E1, 1 times E2, 0 times E3, plus 0 times E4. Now T of E2, this is again equal to 1, 1, 0, 0. So again, this is equal to 1 times E1, 1 E2, plus 0, E3, plus 0, E4. And now T of E3. Now this is equal to, so this is minus 1, 1, 2, 1. So this is minus 1, 1, 2, 1. Now in the standard basis, this is minus 1 times E1, 1 times E2, 2 times E3, plus 1 times E4. And the lastly, then T of E4. Now this is equal to, this is 0, 0, minus 1, 2. So this is 0, 0, minus 1, 2. So this can be written as 0 times E1, 0 times E2, minus 1 times E3, plus 2 times E4. So thus the matrix of T related to the basis beta has its first column as 1, 1, 0, 0, which is this first coordinate vector 1, 1, 0, 0. Then second column is also 1, 1, 0, 0. So second column is 1, 1, 0, 0. The third column is minus 1, 1, 2, 1. So it is minus 1, 1, 2, 1. And the fourth column is 0, 0, minus 1, 2. So therefore, this can be partitioned as, this is here the matrix of TW related to basis beta 1. This is 0. Let's call this as B1 and let's call this as B2. So therefore, we have partitioned the matrix here on this line and along this column. So then, therefore, the characteristic polynomial of T, this is equal to determinant of this matrix 1 minus x, 1, 0, 0, 0, 1 minus x, 0, 0, and minus 1, 1, 2 minus x, 1, and 0, 0, minus 1, 2 minus x, which can clearly be seen to be equal to determinant of 1 minus x, 0, 0, 1 minus x, which is this part, then into determinant of 2 minus x, minus 1, 1, 2 minus x. So therefore, this is equal to 1 minus x whole square into determinant of 2 minus x, 1, minus 1, 2 minus x. So thus, and this part, this is the characteristic polynomial of TW. So thus, T characteristic polynomial of TW of x divides the characteristic polynomial of T. Now let's take another theorem. Let T be a linear operator on a finite dimensional vector space V, and let W be the T-cyclic subspace. Let W be the T-cyclic subspace of V generated by a non-zero vector V in V, and let dimension of W is equal to K. Then the set then let's suppose this part number A, then V T of V, T square of V, so on up to Tk minus 1 of V is a basis for W. Is a basis for W. Then the second part is if A0V plus A1 T of V plus so on plus AK minus 1 Tk minus 1 of V plus Tk of V is equal to 0, then the characteristic polynomial then the characteristic polynomial of TW is C of x, which is equal to -1 power k, then a0 a1x plus ak minus 1 xk minus 1 plus x power k. So we have to prove these two parts on a finite for a linear operator T acting on a finite dimensional vector space V, and W is a T-cyclic subspace generated by V. Okay, now let's start the proof of part number A. Now, since this V is not equal to 0, since V is not equal to 0, so thus the set containing a single non-zero vector V is linearly independent. Thus the set is linearly independent. This is because we know that a singleton set that contains a single non-zero vector is always linearly independent. So now in order to construct this kind of a basis for W, we will keep on adding the vectors into this set. So we have started with this set, which is a non-zero vector, and so it is linearly independent. Now we will try to include more vectors of this form into this set, T of V, then T square of V, then T cube of V, and so on, and see what is the stage so that this set remains linearly independent. So first we will insert T of V inside this set and check its linear independence. Once it remains linearly independent, then we will put one more element, T square of V, into it, and again check its linear independence. And in this way, we will keep on adding the vectors into the set until it becomes linearly dependent. Because this we can do because we know that this linear operator T is acting on a finite dimensional vector space. So this filling of more and more vectors into the set will terminate after at most dimension of V number of terms. So if dimension of V is equal to n, so therefore this process will terminate after at most n terms. But we will show that this process will terminate only after k terms, where k is the dimension of W, and we will show that this therefore forms the basis for W. So now let j be the largest integer such that beta, which is equal to this set V, T of V, so on up to Tj minus 1 of V is linearly independent. So therefore what we have done, we have added vectors into this V, and we are assuming that this j is the largest possible integer such that we can keep on adding the vectors into this V and the set remains linearly independent. So therefore this j being largest means that if we add one more vector into the set, then it will become linearly dependent. But now this j exists. This j exists because dimension of V is finite. So therefore this process has to terminate at some stage. Now let's construct a subspace. Now let Z be a subspace which is spanned by this set beta. Then since this beta is a linearly independent set. So therefore, this beta must be the basis for Z. So since beta is linearly independent, thus beta is a basis for this subspace Z. Furthermore, we claim, this Tj of V belongs to Z. So actually this Tj of V also belongs to Z. If not, then this Tj, if Tj of V is not in Z, then Tj of V belongs to V, but Tj of V does not belong to Z. So we will show that this Tj of V is inside Z. If it is not, then this Tj of V is inside V, because T is a linear operator from V into V, so therefore Tj of V will be an element of V. And Z is a subspace, and we are assuming that this Tj of V is not in Z. But then this Z union Tj of V, which is equal to this set V, T of V, so on up to then Tj minus 1 of V, and then we have this Tj of V inside this is also linearly independent. Which is contradiction to the fact that we have chosen this J to be largest, which contradicts that J is the largest. J is the largest positive integer such that the set V T of V up to Tk minus 1 of V is linearly independent, because we are assuming that this J is the largest integer such that this set V T of V Tj minus 1V is linearly independent. So therefore, if this Tj of V is not inside Z, then this is linearly independent vector itself. So it's a linearly independent set. But then if we include this Tj of V inside this beta, then this set is, then we get a bigger set than beta, which is also linearly independent, and that contradicts the largest property of Z, largest property of G. So thus this T J of V, this must be an element of Z. Now let W be an element of Z. Then since beta is the basis, of Z, we have this W. This can be written as some B0 times V, B1 times T of V, plus so on Bk minus 1 times of Tk minus 1 of V. Because whenever we have something in Z and we are given the base of Z being beta, so therefore this W can be written as a linear combination of the vectors in the basis beta. So therefore we can find scalars B0, B1, Bk minus 1 such that W is equal to B0 V, B1 T of V, and so on, then Bk minus 1 T, K minus 1 of V. Now on this element W, which is an element of Z, we will apply the linear transformation T. So then T of W this is equal to T of B0 of E plus B1 T of E plus so on Bk minus 1 Tk minus 1 of E. But now since T is a linear transformation, so therefore this can be written as B0 T of E. Then B1 T of E, so that can be written as T square of E. And then so on, and this is equal to Bk minus 1, then T of Tk minus 1V is T of Tk of V. But now let's look at these vectors, T of V, T square of V up to Tk of V. They are all the vectors from Z. So therefore this element is an element of Z because this T of V, T square of V, so on up to Tk of V. They are all the elements of Z. Because we have already this T of V, T square of V up to Tk minus 1 of V. They are the elements from the base of Z, and now Tk of V is also an element of Z that is shown just earlier. So therefore, these are all the elements of Z. So therefore, their linear combination is an element of Z. That means T of W is an element of Z. Now this W was chosen arbitrarily from Z. And we are seeing from this equation that T of W is also an element of Z. So actually this equation gives us, thus we obtain this T of W. It is contained in W. So that is W is a T-invariant subspace. W is a T-invariant subspace of V. So but W is the smallest subspace actually we should write now here. Now W is the smallest subspace containing V. Containing V because W contains V because W is a T-cyclic subspace generated by V. So therefore V belongs to W. So W is the smallest subspace containing V, and as V belongs to Z because this Z has its basis as V T of V up to Tj minus 1 of V. So therefore this V is also an element of Z. Thus, and W being the smallest subspace containing V, and V is in Z, so therefore this means that W is contained in Z. But by definition of W being a T-cyclic subspace, generated by V, we have this Z is contained in W. So actually this fact comes from this Z is actually generated by V T of V up to Tj minus 1 of V. But W is a T-cyclic subspace. It is the span of V, T of V, T square of V, and so on. So therefore there is no restriction on that powers of T. So therefore clearly this span of W also contains all the elements which span Z. So therefore Z must be contained in W. So therefore from these two equations, W is subset of Z and Z is subset of W. Thus we obtain W is equal to Z. So thus we have W is equal to Z. So then dimension of W is equal to dimension of Z. But now Z is generated by J number of vectors. So dimension of W is equal to J. So let J is equal to K. And we are done. So therefore this completes the proof showing that V1 T of phi, V T of phi, T square of phi up to T K minus 1 of phi forms the basis for this T-cyclic subspace W. Now let's come to the part number 2 of this theorem. Now let beta equal to V T of phi up to Tk minus 1 of phi be the basis for W. Be the basis for W. And let A0, A1, AK minus 1 be the scalars such that this A0V plus A1 T of phi plus A2 T square of phi plus so on AK minus 1 Tk minus 1 of phi plus Tk of V is equal to 0. Now in part number 2, what we have, we are given that this A0V, A1 T of V, AK minus 1, Tk minus 1V plus Tk of V is equal to 0. We have to show that the characteristic polynomial of this restriction linear transformation is this thing. So we have this thing. So then the matrix of TW, related to this basis beta. This is a matrix whose columns are T, the coordinate vector of TW of V, related to the basis beta. Then the second column is the coordinate vector of TW of T of V, related to the basis beta, and so on. And similarly, the last vector is TW of Tk minus 1 of phi related to the basis beta. So now we will evaluate these coordinate vectors related to the basis beta. So now this T W of phi. Now since this TW is a restriction of the linear transformation T from V to W, so TW of phi can also be written as T of phi. So T of phi is same as TW of phi. This is by the definition of, because TW is just the restriction of this linear transformation T from its domain V to the domain W, which is its subspace. So therefore, this is equal to, now we have to express this in the linear combination in this basis beta. So we can write it, it is 0 times V plus 1 T of phi, then 0 T square of phi, then so on, then 0 T K minus 1 of phi. So also T W T of phi, this can be written as T square of phi. Now this is equal to 0V plus 0 times T of phi plus 1 t square of v plus so on plus 0 times tk minus 1 of v. So then, and so on, this tw of tk minus 1 of v, so tk minus 2 of v, this is equal to tk minus 1 of v. So in the basis beta, this can be written as 0v, 0 t of v plus so on, 0 t k minus 2 of v plus 1 tk minus 1 of v. And lastly, t w of tk minus 1v. Now this is equal to tk of v. Now this tk of v can be obtained from this given polynomial. We have this tk of v is equal to minus a0v minus a1t of v minus a2t square of v, then minus ak minus 1 tk minus 1v. So this is equal to minus a0v minus a1 t of v, then minus so on, minus a k minus 1 tk minus 1 of v. So thus the matrix of T, thus this T W related to the basis beta is a matrix supported K cross K, and its first row column is the coordinate vector of T W of V, that is equal to 0 1, then 0 0. So this is 0 1 0 0 and so on, 0 0. And similarly, the second column is the coordinate vector of TW of T of V, that is 0 0. Then the third one, this is 0 0 1 0 0 0 and so on. This k minus 1th column, that is 0 0 0, and now here we will have this entry 1, and then the last is again 0, and the last column is this minus a0 minus a1 minus a2 minus a3, so on. This is minus ak minus 2, and this is minus
it's 8 o'clock.
ak minus 1. So in fact, we can see that which is the companion matrix, which is known as a companion matrix. Companion matrix. So thus, the characteristic polynomial of TW is, it is C of X, and this is the determinant of this matrix, which is determinant of A minus Xi, where A is a companion matrix. Where A is a companion matrix. And we know that its characteristic polynomial is given by that formula. So therefore this is equal to minus 1 power k into x power into a0 plus a1 of x plus a2 of x square plus so on plus ak minus 1 x power k minus 1 plus x power k is equal to 0 plus x power k. So this is the characteristic polynomial of the companion matrix. Now, in fact, this can also be proved using induction on k. So this completes the proof of this result.